Hello friends, I am Sheetal Shalke. In this video, we are going to discuss one example of a linear equation with regular singular point. So the example is, if u of x is equal to x square minus 1 raised to n, then prove that um at 1 means mth derivative of u at 1 equal to mth derivative of u at minus 1 equal to 0. If 0 less than or equal to m less than or strictly less than n. So the solution of this example is, here we have given that u of x is equal to x square minus 1. So let given u of x is equal to x square minus 1 raised to n. Okay, so this can be also written as, here we use the formula a square minus b square. So this can be also written as x plus 1 into x minus 1 whole raised to n. So using the law of indices, this can be also written as x plus 1 raised to n into x minus 1 raised to n. So our u of x is equal to this. So for finding at 1 means mth derivative of u at 1, we have to differentiate equation 1 with respect to x m times. So taking mth derivative of this, for taking mth derivative of this, we have to use the Leibniz rule. Leibniz rule for product of two functions. So if u and v are two functions of x, then their mth derivative is equal to mc0 u m v plus mc1 u m minus 1 v1 plus mc2 u m minus 2 v2 plus and so on mcm u into vm. So using this Leibniz rule here, we have to find the mth derivative of u. So taking mth derivative of equation 1, taking mth derivative of equation 1 using Leibniz rule, we have um of x is equal to, so mc0, the value of mc0 is 1. By using the formula, we know that mcr is equal to m factorial upon r factorial into m minus r factorial. So using this formula here, we can easily find all the coefficients of Leibniz rule. So it is equal to x plus 1 raised to n, its mth derivative, into x minus 1 raised to n as it is, plus the value of mc1 is m, and into x m into x plus 1 raised to n and its m into and its m minus 1th derivative into x minus 1 raised to n, its first derivative, plus the value of mc2 is m into m minus 1 upon 2 factorial into x plus 1 raised to n and its m minus 2th derivative into x minus 1 raised to n, its second derivative, plus and so on. The last term mcm, the value of mcm is 1 and x plus 1 raised to n as it is into x minus 1 raised to n, its mth derivative. So it is equal to, now taking mth derivative or finding mth derivative of this term, this mth derivative of x plus 1 raised to n will be n into n minus 1 into n minus 2 and so on, n minus m minus 1 into x plus 1 raised to n minus m into x minus 1 raised to n plus how we can find the mth derivative in this way, as we know that if you finding first derivative of x plus 1 raised to n, then it will be, if you finding its first derivative, then it will be n into x plus 1 raised to n minus 1. If you finding its second derivative, that is x plus 1 raised to n, its second derivative will be n into n minus 1 into x plus 1 raised to n minus 1. In similar way, if you finding its mth derivative, it will be n minus 1, n minus 2 and so on, n minus m minus 1 into x plus 1 raised to n minus m. Okay, so plus m into its x plus 1 raised to n into m minus 1th derivative. So it will be n minus 1 and so on, n minus m minus 2 into x plus 1 raised to n minus m minus 1 into x plus 1 dash. So its first derivative will be n into x minus 1 raised to n minus 1 plus and so on. The last term x plus 1 raised to n into x minus 1 raised to n, its mth derivative. It will be n minus 1, n minus 2 and so on, n minus m minus 1 into x minus 1 raised to n minus m. Okay, so this is the mth derivative into, okay, that will be written already, we have that will be already written. So this is equal to, okay, this is our mth derivative of u at x. If we put x is equal to 1 here, if we put x equal to 1 here, then this term will be vanishes. Here this term will be vanishes. In mth derivative of of x, in each term there will be x minus 1 the term. So if we putting x is equal to 1 in this equation, so all term will be vanishes. So the, if we putting x is equal to 1 in equation 2, then RHS equal to 0. Similarly, if we putting x is equal to minus 1, if we putting x is equal to minus 1 in equation 2, as we know that in each term there is a x plus 1 term. So if we putting x is equal to 1 here, so RHS equal to 0. Hence, of 1 equal to of minus 1 equal to 0. Hence, the proof. Okay, thank you.